So very welcome back, and also welcome the new students to listen to the lecture of reinforcement learning part 2. So my name is Zhongwen Xu. I'm from CA Lab. So I think in the first part of the lecture, we introduced a lot of the key concepts in reinforcement learning, including like what really reinforcement learning is, like what kind of problems it is solving, and like what kind of like important components, including in the reinforcement learning agent, which are like the policy, the value, and also some of the reinforcement agent. They include the models, which is the understanding of the agent of the environment. So next, in the second part, I'm going to really tell you how we can use reinforcement learning, like what are the actual reinforcement learning algorithms can be applied like nowadays. So the first really important concept in reinforcement learning is temporal difference learning. So it's a way to help the agent to learn the value function. So due to the time limit, I have to go through many things. I will briefly introduce the Monte Carlo prediction first. So the Monte Carlo prediction means that Monte Carlo methods, I think, is widely used in statistical learning, and Monte Carlo means like the method is relying on random sample. So here, the very brief like equation here is that it is updating the value function of state S. So according to the error between two variables. The first one is a GT. So recall that in the first part of the lecture, GT means the episodic return. So it's from time step T forward till the end of the episode, the total sum of the return. So here is indicating that we take the sample from the current time step and then just run the policy forward, collect all of the rewards in between, and then sum them with the discounted future steps. And then we have the GT. So the GT indicate like from time step T till the end of the episode. And the value function V of ST is the current estimation of the value function of the current time step. So with the difference between these two, we can have the error, and then also applying by the learning rate alpha, because you will not. So even though like the GT is like a sample from the current time step to the end of the episode, you will not like to update the VS towards the GT like immediately. So it's not, instead of like using an learning rate of 1, which will really make like GT, really make like V of ST immediately equal to GT. Instead, we update in a small learning rate, like alpha might be like 0.01 or even smaller, 0.001, something like that. So in this form, so the key of the Monte Carlo method is that we, starting from the current time step, we sample the future interaction between the agent and the environment, collect all of the rewards in between, and then obtain this like actual return. And then use it for learning the values. And instead, in temporal difference prediction, so as we will see later why it is called this name. And from this equation, we can see that, okay, the return disappear from the equation. Instead, introduce a form that we use the reward of next time step. So it is RT plus 1, and then plus discounted and the value of the future state. So instead of like actually running the policy till the end of the episode, we use an estimation, which is using like next time step reward plus all of the future steps is summarized in the value function of the next state. So recall that we also mentioned the recursive form of the return and also the recursive form of the optimal value function. So here is like in a similar form, which is that your current value of the current time step should be equal to the reward from the next time step plus a discounted future values. So for the temporal difference prediction, I think you can sense that. So these are like the two different time steps, and the error is obtained by taking a difference between these estimation from the next time step and the current prediction of the current time step. And then again, similarly, we apply a small learning rate to update the current value towards this estimation. Next, still like in the temporal difference learning, a very key concept is called the TD error. So this is the equation we take from the previous slides, and it is updating the value function of the current time step as we just mentioned. Very important concept here is that we take this full form out and define it as a new name. It is called like TD error. So the TD error is that this one, the future time step reward plus the discounted future values. This is an like update target. So it has an official name in the reinforcement literature. It is called the TD target. So the target is so this one, and then we have the current estimation, which is the current prediction V of ST, and then the difference between them, it is called the TD error. So it is called like delta at time step t. And here is a very important equation in, oh, there's a question. Why do we write RT plus 1 and not RT? So we briefly mentioned this in the part 1 lecture. So we are following the convention from the Introduction to Reinforcement Learning book, which is so Sutton and Battle. They define this convention like the reward, which is caused by the action from the time step t. The reward is called from, it is named like RT plus 1. So it's that it's just a convention, but like many people follow this convention. There are other conventions which is namely use RT to denote the reward caused by the action AT. But I think in the lecture and also like many literature, we are following this convention. So action AT feed it in the, so remember the agent environment group. So the action AT will be fed into the environment. The environment will produce two things. One is the reward, so it is RT plus 1. The other is the state, so it is ST plus 1. So it's a convention, yeah. So let's continue. I also like feel free to ask any questions in between. So this important equation, it is telling us a very important property of the TD errors. So the equation says like the return from time step t minus the current estimation of the value, which is the V of ST. It is equal to, like you can see very easily, this is the recursive form of the return. right? So it can expand the GT into the reward from the next time step and then a discounted of the future return. And then still the minus VT, right? And then we append like two items here. So one is like plus and then it is like minus, the same thing. So it is the discounted of the future values. And then we can see that this one is the TD error. So as we can see, right? Sorry, so it's this one, RT plus 1 plus gamma times VST plus 1 minus VST. So this one is essentially the same as the, sorry, this guy, right? So it's defined as the TD error. So we accumulate this this item, and then this one to the TD error, and then we leave like these two left, right? So we extract the gamma out, and then further we use the same thing to further expand. So you can sense like it is a recursive form, and then it's adding like another gamma into the equation. And then we continue to expand the whole equation until it reach like the end. The end is like the definition of the end of the episode, the future return, and then the value, they are all zero. So as we can see, like all of these equations only consist two things. One is the TD error, so it's the delta T, right? You can see like the time index keep increasing from the T and then till the end of the episode. And then there's another thing is the discount factor. So the power of the discount factor also keep increasing from like 0 to 1 and then to 2 and then to like this T minus T minus 1. So this is a very useful form, and we will see them like in many reinforcement learning papers if you like continue to study the field. So it is telling us that the difference between the return and the predicted value is a sum of the discounted TD errors. So next one is the concept of bootstrapping. So arguably, this is one of the key ideas in the field of reinforcement learning. So it comes from the TD learning so why it is called bootstrapping? Because like the whole iteration of the value function, it is starting from like random. So it starts from a random estimation of the values for all of the state, and then gradually it uses this equation to iterate and attain the optimal value function. So how it achieves so? It does not rely on like instead of like some classic example in like supervised learning case, you may think that we have like regression. You have a like actual oracle target. You can regress your value function towards. So it is not the case in the TD learning. What it does is that it is learning from an accurate estimation. So to learn the current estimation of time step t, so it is the v of st, it is using the value function itself, but on another time step. So it's on the next time step using the same like inaccurate value function, but apply on the next time step. Use this discounted sum as the target to learn the current values. So it is learning the value function from an inaccurate like estimation of the value. So sometimes people say it is like it's learning from a guess. So you are guessing what's the values And also, yeah, based on your guess of the next time step, you are learning what's the value function of the current time step. But this is a very important concept because it allows you to like without any oracle of the value function, like keep iterating and keep learning from your from the future estimation. You can your value function can become more and more accurate. Next, so previously, all of these methods, including TD and Monte Carlo prediction, what they are doing here is that they are trying to learn a value function of a state. So, so that like given a policy, you can like evaluate this policy, like under this policy, how much the future as expected cumulative reward the agent can attain. So it tells nothing about like how you should act in certain state. So it does not have any concept of action, as you may have noticed. So there's no action in the formulation. So it does not tell you how you could choose for example, action to the left or to the right. Like it does not tell you anything about that. And next one, we are going to explain the algorithms which allows you to make like decision. So essentially like let you to choose what's the current estimated best action to act at the current state S. So the first algorithm is called SASA. The algorithm is the equation is again quite simple. So it looks very similar to the TD prediction in the value function case. Instead of like using state value function here, SASA equation use the action value function. So like you can sense that replacing all of this value v of st plus 1 and v of st, replace them with the q values, which include the action in the input. So similarly to the so it's also a form of like TD learning, but it's used in the control case, which is helping the agent to make decision. So the learning of the Q values here is also based on bootstrapping. So the learning of the current Q values at the current time step T of the state and the action AT is based on the estimation of the Q values of the next time step. So they are like ST plus 1 and AT plus 1. And then like similarly use the discounted sum of the future reward plus like the discounted estimation of the Q values of future state and the future action. You can update your current Q values towards that. So and I put this tuple here. I think maybe you can guess why this algorithm is named SASA, because it consists of tuple of like these 5 characters. So state, action, reward, and state, action. So this describes the whole equation. So here is a tiny like algorithm description box, which describe like how briefly we can run this algorithm. So I think essentially is the same thing as the equation, as you may have noticed from this line, but it's equipped with more interaction between the agent and the environment. So we have another algorithm in the TD like control, which is again using the bootstrapping to learn the Q values, and so that you can make decision in the current time step. and based on the state. Another very famous and helpful algorithm is called Q-learning. So the name comes from actually the Q values. So here again, similarly, if you would like to update your Q values of the current state and on some action AT, the update rule becomes this one. So it is, instead of using the let's check the Sasa equation again, right? Instead of using the exact action from the next time step as the bootstrapping Q values, Q-learning use another one, which is the maximum of the Q values among all of the action. So it's not taking the actual happen action. It's using the one with the maximum Q values. So yeah, similarly to the Sasa learning, this can give you the estimation of the Q values of all of the state and the actions. As you may notice, we put an notation of policy here. So let me explain a bit on what is on policy and what is off policy. So there are two policies. If there are two policies, we can denote them in this form. The first one is learning policy, which is also called the target policy. We denote it as pi. And the other one is behavior policy, which we denote it as mu. So behavior policy is the one we use to interact with the environment and also to collect data. And then the learning policy is the pi, which is the policy we keep updating. So the concept of on policy and off policy, the really difference is that they you can see that they could be the same. So you could use the same policy, which is mu equal to pi. So to use the learning policy to collect the data, to only use the learning policy to interact with the environment. So that in this kind of algorithm, it is called on policy algorithms. Instead, if you are using policy mu, which is different from the learning policy pi, they will be called off policy algorithms. So which means that you are using different from the pi, you are using either some a variant of the learning policy pi. For example, you could use epsilon greedy on the policy pi. So it's normally you will use the action sample from the learning policy pi, and every so often you sample with certain probability, sample a certain random action. So your behavior policy will become your learning policy pi plus some epsilon greedy policy. So it's different. So in that case, the algorithm will be called off policy algorithms. And why is it important? It sounds like it would be great if every time you use the same learning policy to collect the data and use the same policy to interact with the environment. Why is it important to study off policy algorithms? Because it allows the learning to happen in many different scenarios. It's a bit restricted to us the behavior policy, which is used to collect the data, to be exactly the same as the learning policy. And if we open this up, the algorithm and the interaction has a lot more flexibility and possibility. So again, going back to the equations, we can really like see the key difference between Q-learning and SASA lies on the this formulation of the update target. So SASA use the actual next time step S t plus 1 and also the action AT plus 1 and use the Q values to obtain the target. And instead in Q-learning, we use a maximum of the Q values among all of the actions. So instead of taking the actual action, we use the current best estimation of the next Q values. Again, this algorithm description box describe the complete picture of the Q-learning algorithms. So the key equation is here, and also it also includes certain like interaction between the agent and the environment. Cool. So there's one question from Ansel. Here we are assuming policy is deterministic. No. The policy is I think stochastic. Yeah. So actually in the algorithm does not say anything about that because I think the equation is quite general, and typically people actually in all of the examples in my lecture, they are mostly like stochastic policies, which means that you can have a pi function, policy function pi over your state S, and then the output is a distribution over the action. So that you can, for example, you can have a softmax distribution, and then you can sample from it. And for the Q-learning cases, you can see that if you always take the action with the maximum Q values, it's a greedy policy. However, typically people use the greedy policy equipped with the epsilon greedy exploration. So it will become a stochastic policy. So second question, can we use value function from TD prediction to learn a policy? No, without the actual model. So as you can see, the formulation of the value is only on the state. So it does not have any, so it cannot tell you like action left or action right, which one is better, right? So it only can tell you in the current state as T, and then if the agent is following the policy pi, what kind of like future cumulative reward it can attain. So that's the definition of the value function. And instead, people have to use action value function, which include the action as input. So for example, you have like QS A0 and QS A1, right? So if one is like, let's say the value is like 0.9 and the other one is 0.2, and very naturally you can use the action with higher Q values to be the greedy policy. Cool. Hope that's clear. Okay. On the there's some issue. So yeah, on the second part, I'm going to introduce a very modern instantiation of the Q-learning I just talked about, and also a very practical way to use like the idea of TD in the real world like scenarios. So the deep Q-learning network, which is also called DQN, as you may have heard about. So it was published in Nature 2015, it was the very first breakthrough in deep reinforcement learning. So so you can consider deep reinforcement learning as a field which combine deep learning as the representation. So use neural networks to represent the agent, and also including to represent the policy and to represent the value function. Also, it has the key concept of reinforcement learning. So study the prediction, study the control, and this deep Q-learning network paper really made people realize the ideas of the reinforcement learning, which was actually most of the ideas were including Q-learning, and also the later in the introduction of the later slides, including the method in the policy gradient, they were introduced in the 1990s or even 1980s. The idea of TD, for example. So these ideas were proposed many years ago, but until the deep Q-learning network, people really and researchers really make it work. So before that, reinforcement learning can only work in very simple environment. For example, the toy domains in the RL book. So they are mostly some Greek words. The agent starting from some starting state and then end to the another state. So similarly in the example of the maze I gave in the part 1 lecture. So reinforcement learning before this deep DQM paper, it was not considered as great algorithms, or no one really expect that can work in video games. So let's briefly talk about this first breakthrough in the deep reinforcement learning. So we just talk about the concept of Q-learning. So the key concept of Q-learning is that it can help the agent to learn an action value function Q of SA, and then the definition again to reiterate again. So it's the expected return at the state S when it is taking the action A. So what does this Nature 2015 paper really does? What makes it really different from the reinforcement learning work in the 80s and the 90s? There are many key components to make it work. I think we will go through some of them here. The first one is to use deep neural networks. So as I already mentioned, it is marked as the start of the field, deep reinforcement learning, and it wasn't really the first paper to try neural networks combining with reinforcement learning, but it was the first one to really show that learning from pure pixel, the agent can achieve human level performance. And then the second idea is called experience replay. It was proposed in 1993, but it was revived again in this DQM paper to make the learning of Q-learning really stable. And to stabilize the Q-learning, there's another technique called target network. We will talk about it later. So similarly to the experience replay, the goal is to make the learning the goal is to make the Q-learning much more stable. And finally, I think the success of DQM could not be there without the many developments in the deep learning field, including some modern optimizers like OAMLS prop. So all these important pieces put together and then make the breakthrough in the DQM paper. So let's see what we can what we can really apply Q-learning combined with the neural network. So the first of all, the update rule here, which we have been using in the previous slides, including in the first part. So all of these cases apply to some simple environment. So they are called like tabular environment, which means like each state is really discrete, and also you can even like name or number the state. So for example, in the exploitation case, there are like a different slot, and each slot is a state. So they are really, you can really denote all of the Q values and all of the state in some of the like tabular form. So in that kind of tabular form, you can directly update your Q values according to this kind of update function. However, in the neural network case, which actually in a most general sense, as described in the reinforcement learning book, it is called like in the approximate case, which means like the state, the Q values of the state might be possible to generalize to other state. So in order to do that, we use a like parameterized form of the Q values. So here, as you can see, so it is denoted as the Q of the Q values is parameterized by the parameter theta. So still taking the same input of S and A. However, instead, it is using the parameter theta to parameterize the Q values. So instead of using the direct update route in the deep learning cases to train a neural network, people typically form the update in a form of a loss function. So we rewrite this update loop into the loss form, which is again the next time step reward plus discounted of the Q values of the next time step, and then taking the max over the action. So use this one as target, and then you can view this as a regression loss. So from the Q theta of the current time step regress towards this target, and then we can sum this loss over a batch of examples, and then take gradient descent on this loss. So that's the core idea to transform the classic Q-learning from the tabular case into the modern deep learning usage of the approximate case. So here is an illustration picture from the paper, which describes like what the neural network really look like. So it comes, the input is pixel, so the pixel screen input, and then with certain, actually there are quite a lot of complicated wrappers to transform the original input to the input of the neural network. And then after that, it will go through like several layers of convolutional layers, and then produce some hidden layers. And then it will go through another 2 layers of fully connected, output the Q values for all kind of different actions the game can possibly make. So so as you can see, like the input is pixel, and then the output are the Q values of the possible actions. So the first natural question is that why do we use neural networks? Because it can really, in the past like decade, the research in the deep learning and neural network really tell us like neural network are really good at learning the gray representation. So prior to the DQN work, there's actually some work which handcraft the features for the Atari input. So the researchers use some human knowledge to design the input to the linear layer. However, I think from this paper and so on, people all switch to using neural networks because learning the future by pure gradient descent is much better than relying on human heuristic to handcraft the features. And they are really efficient on the modern hardwares, including the GPUs and the TPUs, and using this as a representation of the agent, they can be really generally applicable. So for example, in Atari, there are a bunch of the games. So if each of the game require like handcraft features, like the people have to know the game very well to design what kind of feature will work best for each of the game. So it is a very time-consuming process, and also it's not transferable. It's not a general solution. So starting from the DQN paper, the deep reinforcement learning can really become like a single solution can be applied on many different games. So let's see how we can use neural network to represent the Q values. There are two ways to do that, and actually, like the DQN use the second way, and let's see why it is the case. On the left, so there's one possible to parameterize the Q values of S and A is that the input take a tuple of state and action. So the action can be represented as like one hot vector, and the state is another vector, or the like 2D or 3D tensor. They can be fit into the neural network, and then to obtain the Q value of S and A, we can just ask the neural network to produce a scalar output. So in this case, the input is a tuple, like has the full information of what it is asking for, and predicting one scalar for it. The other like possible way, which is used in DQN, is that we only feed the state as input. And in the output, instead of only producing one scalar for one action, we produce all of the scalar, like a vector output for all of the possible action. For example, here we take a minimal example as like 5 actions. So from one forward pass of the neural network, from the state, you can obtain all of the 5 like actions. So perform one forward from the state, you can have like QSA0, QSA1, and then to QSA4. So all of the 5 scalars can be obtained at the same time. So as you can imagine, if we would do the same thing from the left-hand side approach, you have to enumerate the different action. So from the first action to the 5th action, feed each of them as input, and then we have to perform the forward pass of the network 5 times. So it's much slower than the right-hand side. Okay, question? How do you account for the possibility of different lengths of action vector for different state? So in a typical scenario, the action space is fixed along the training of one environment. So it's you can think it as like predefined. So it will not happen in the case of what you described. Yeah, cool. Okay, so on the second like important component in the DQN is called experience replay. So experience replay is a currently widely adopted technique. So it's you can see the functionality of experience replay in the illustration. So from the bottom, there's an interaction loop between the agent and the environment. So the agent send the action to the environment send like observation or state back to the action. Along the way, the agent will accumulate the interaction experience between the agent and environment, and then they can send it to a storage buffer, so which is called like replay buffer. And how do the agent perform the learning is that it samples from the replay buffer to obtain a batch of data. So you can imagine like it has like the all of the transitions between the agent and the environment, they store here in the replay buffer, and then they perform batch iterated update in the learning side. So from this part, the iterated loop is like very similar to supervised learning. So in supervised learning case, the model or the neural network, they iterate from a data set. So the replay buffer here act as the similar role as the data set. So the agent to perform the learning, and so it can construct a loss and then iterate over the replay buffer. The data structure of the experience replay is like a transition tuple. So we can see here, so it's the actual data structure used in the implementation of experience replay. It store like the current state, the action, and the reward of the next time step, and discounting of the next time step, also the state of the next time step. If you store this kind of transition into the experience replay, you can perform like these different operations of the replay buffer. First one is to add the transition to the buffer. So in the sense of like pseudocode, you can see it as like you have a buffer. The buffer can append the transition in the tuple form into the buffer. And the second important operation is that to perform the learning, the learning agent can sample a batch from the buffer. So it can simply call like buffer.sample, and then it can obtain like a batch of these tuples to perform the learning. Also, because like the buffer is not like unlimited. So because the interaction between the agent and the environment can be huge, so it cannot store everything. And also for the obsolete experiences, the agent does not need to learn from that because like you can imagine the agent can become stronger and stronger, and the very beginning experience when the agent is random is not needed in the later stage of the training. So there's another operation to remove these obsolete experiences from the replay buffer. And for the target network, so the key idea here is that we have to, so in the like 90s, when people investigate like Q-learning, they've often found like the Q-learning is not very stable. And that is, I think, one of the key reasons like the reinforcement learning wasn't really widely adopted until the DQM paper. And another innovation that DQM paper did is that to stabilize Q-learning, we can see from the equation we derive from the tabular case to the approximate case in the neural network. Instead of using the Q values from the same parameters of the learning Q values. So as you can see, this one, so they are the same. So these Q values of the next time step as t plus 1 is using the same parameter as the Q value of the current estimation. Instead, we use another network, which is called target network. So you can think it as simply like another neural network, which is which every so often it will update to the up-to-date Q-value network. So the role of the target network is to make the learning stable. So let's think about why it is unstable in the first case. In the changing, like the theta is keep changing along the way of the training. And to learn the Q Q values with the parameterization of theta, you are using the same theta as the target. So you can think it as like you are regressing. The Q values is regressing to certain target. However, the target is also changing quite dramatically, and it will easily cause like instability. Instead of using the same like fast changing parameters as the Q value parameters, we use another like relatively slowly update, and we could fix it for quite a long interval. And then the target can be much more stable. So the target network update, there are two different ways. The first one is hard update. So every like M iterations, we copy the current Q network parameters to the target network. The other one is called like soft update, which is we keep updating the target network, but with certain parameters alpha. So for example, we can use a very slow update alpha as like 1/1000. So essentially like moving really slowly to the up-to-date parameters. So both methods work very well. And there are many developments since the Nature DQN paper, including like double DQN, prioritized replay DQN, and a really combination of all these techniques is widely adopted as a good baseline nowadays. It's called Rainbow DQN. And then also to speed up the training of the DQN family agent, people use distributed training in the distributed prioritized event replay paper. Also later, people find out that in the replay, if you introduce the recurrent neural network, the agent could perform better, and they introduced this like R2D2 paper. So there are many developments like from the classic Nature DQN, they all happen in the past recent years, and still like people are still studying it and improving that. And there are some very good reference implementation of the DQN family methods. So they're very kindly provided by the original authors and the team in DeepMind. So it is provided in this link, the DeepMind DQN Zhu. They try, so it's not the original implementation, but the research engineer tried very hard to reproduce the result, and they managed to do that. So and the code base is very clean. They can run on like single GPUs and do not need to worry about the resources much. And I think it's a very good place to learn about all these of like great agents. Okay, next, I think as requested by the students in the first lecture, I would spend some time and to walk you through how to really implement an reinforcement learning agent. So there are a few key important parts. The first part is like the environment APIs. And the second one is the agent environment loop, which is the essential of the interaction between the agent and the environment. And the final bit is about the learning. So for the environment APIs, here I'm using the DeepMind environment API as an example. There are actually another very popular API is the OpenAI Dream API. They are quite similar in the flavor, but I will just use the simpler DeepMind API as an example to walk you through the lecture. So the DeepMind environment API describes some essential like data structure and APIs for the reinforcement learning environment. So there are a few key components. First one is environment. So this is an abstract-based class for all kind of reinforcement environments, and then a class, and it is a container, which is called timestamp. So it contains some very important variables output from the environment. And there are other important concept called specs, which is the you can specify the shape of the observation, the shape of the reward, and such. So let's go into more details. So the environment APIs and the interaction between the environment and the agent is actually quite simple, and it reflects the agent environment interaction loop. So on the very first step, we reset the environment to the very starting point, and then it can output the time step. So it is an output from the environment. And then the loop starts, the agent can step according to the time step and produce an action. So you can implement the agent with different methods. For example, you can use the dequant methods or other like policy gradient method. So the mapping from is so the policy is basically taking the time step, produce an action, right? So that's what an agent does, and then feeding back the action produced by the agent to the environment, and then the environment will give the agent the next time step, and then the loop continue to take the agent will take the time step to produce action and then move it forward. And then the time step is a like container which has like all of the essential information from the environment. It includes like step type and reward, discount, and observation. So observation is similar to the state we have been talking about in the previous lecture. So the step type include like whether the time step is the first step or the environment. For example, for this one, so the time step is just obtained after the environment reset. So the time step will have a step type of first. So for the other intermediate time steps, they will be marked as like mid. So it's a middle time step. And when the environment ends, so the episode ends, it will mark the step type as last, so that you can judge whether the game has ended or not. So let's see the agent environment interactions. So yeah, excuse me. So the loop is performing to collect number of sequences. For each of the starting point of the loop, it will first reset the environment, and then the loop begins. So it's similar to the last slide. However, in addition, it has an if statement, which is judging whether the time step is the last time step. So it is saying that whether the environment or the game has ended. If so, it will step it further to mark it as end, so the agent can know it is end and then break the loop. So it's very similar to this one, just with additional if statement on the step type. Yeah, and next we are going to walk through certain really can be used, the code really can be used, so we can learn how you can implement a simple agent. So the first one is from a library called Relax. So it's a reinforcement learning library written in the JAS library. So it provides many helpful reinforcement learning functions, including how to calculate the loss for the double Q learning, and how to calculate more advanced losses proposed in the recent papers. Also provide many functionality in reinforcement learning. I think it's a very good way people can learn how to write code for reinforcement learning. Can you see the screen of the GitHub?
Yes.
Okay, cool. Thanks for confirming. You may also go to the link actually. So you can search that relax and then go to examples and then simple DQM. It's a really complete, however, it's really simple. It's less than 200 lines of Python code, really help you to understand what are the essential parts of building a deep reinforcement learning agent. So let's walk through the code like piece by piece. First one is like, it has some like import some different fancy libraries and define the data structure of certain variables. These are not quite important for now, but for the actual implementation, the first function is like build network. So essentially it's just building like multi-layer perception network with like certain hidden unit and then outputting certain number of actions. So for this one, you can basically, so tell you from the name of the function is the Q values of certain state, and then produce the Q values of all of the actions. So the input is the state, the output is like QSA, including all of the actions. And then, yeah, probably let's go from the training loop first. Yeah, so the first one to obtain environment, which in this very simple example, they use a very simple environment called catch. You can check it out in the GitLab, clicking the import link. And then it specifies some config. So for example, here, specify the epsilon, how the epsilon change along the training. It does not really matter. I think it's a very technical detail. And then use the DQN class to instantiate an agent, which take the observation specification from the environment. So to tell you what's the shape of the input and what's the shape of the state. For example, in Atari case, this observation spec can tell you like it is like 84 by 84, like 10 times 3 channel, something like that. And the action spec is telling you like how many discrete action the agent can perform. So it is essential for the agent to understand what kind of actions it can perform so that it can interact with the environment. And then the epsilon here is just for the epsilon greedy we mentioned in the lecture. And then target period is the period to perform the target level update. And then learning rate is for the optimizer. So after that, we obtain an instance of the agent. And we instantiate a replay buffer. Another experiment can run in a run loop. So it's basically performing the interaction between the agent and the environment and then perform the learning. So in the very high level, right, the implementation is like it has all of the essential pieces we introduced in the lecture. And then let's take a detailed look in the run loop. So run loop basically describes the agent environment interaction. So as you can see, first it reset the environment. So it's a very familiar environment agent loop we just mentioned in the DeepMind environment API. First, the environment reset, and then the agent can obtain a time step. And then there's some accumulator. You can think as like it can accumulate the time step into the buffer, and also it can accumulate the time step to calculate the total return, the total reward, right? So the loop begins like loop until the episode end. So it is why not time step last. Then the first thing is that the agent can add by taking the time step as input. So you can ignore like some of the other parameters for now. So taking the time step from the environment the agent add according to the time step to produce the actor output. So because the agent is acting, we can call it like the actor. So this is the actor step. Actor step means agent take time step from the environment, produce the output. And one of the most important key output from the actor is the action. So take the action out, and then the action will be feedback to the environment. And then the environment will continue to loop and give the agent a new time step. Yeah. And then for the time step, the experience replay, like we keep adding this experience into the buffer. And every so often, like you can make other kind of like if statement or any condition statement. This is saying like when the buffer is ready and to take a batch size of the transitions as well, the agent can perform learning. So here, instead of the actor step, it is called learner step. So learner step basically update the parameters of the agent to a new parameters. And the input to the update is sample from the replay buffer. So it's really implementing what we just have been talking about in the DQN paper, right? So you sample a batch of the transitions from the buffer, then perform the learning. And for the rest, actually is the evaluation details. We don't need to walk it through for now. So is this high level implementation clear for the students? If so, we can continue to some of the details. Yeah, the first one is like, as we mentioned, the replay buffer is the storage of the transition. So you can first like initialize the buffer with certain capacity. So it is not an unlimited storage of the data. It can have some like maximum slot for storing the transition, and for the API, like similar to the append we just mentioned, it name it as like push. I think it's the same thing. So basically, it's just append the current like data, including the observation, the state, the action that is the A, the reward, which is the R, and then discount gamma, and the latest observation, which is essentially the like next time step state, so which is the ST plus 1. So after appended, so basically just do the append, and then so this is when the agent add and interact with the environment, it will append the transition to the buffer. And for the learning, so as you can see in the agent learning step, it will first sample a batch of transition from the buffer. So here we can see there's a like sample functions, which the agent passes like how many data in a batch the agent require for the learning. And then it would just like randomly sample from the buffer to obtain these variables. And then you can pack all of these variables together as a batch, pass it for the learning, for the agent to learn. And yeah, this buffer is actually a very simplified implementation of the more advanced buffer, but it does what the basic requirement of the replay buffer do. And then for the DQN agent, right, it's a very simple one, as I mentioned in the documentation. We're taking observations back, which describe the input shape of the state. We're taking actions back, which is, for example, the agent can perform like 10 different actions. the action spec can tell there are at most 10 actions, so that the agent can decide the output dimension of the Q values. For example, target period is describing like how often you update your target network. We briefly touched that. So this one, for the neural network and the optimizers, they can instantiate it in some very simple APIs. And for the JIT, I think you don't need to care about that for now until you really get deep into this library called JAS. So for the initialization of the parameters, it's just randomly generate the parameters for the agent. Also, for these three things, they are all initializing certain variables. For the actor step, so which is the acting from the agent. So the agent take the environment output, which is essentially the time step. And then accordingly, according to the parameters of the agent itself, the output is the action and the Q values, as you can read from the code. The code is actually quite self-explained. So first of all, take the environment output and observation. So use it as a it's adding a dummy dimension for that. And then if put it into the network, use the online filter to obtain the Q values for all of these input. And then next is essentially performing epsilon greedy. So so it's actually using, there are two different forms. First form is the greedy method. The greedy method use the Q values, just select the maximum action. So use the QSA and then choose the action with the maximum Q values. And then in the training phrases, we have the epsilon greedy method. So essentially you pass a function called epsilon greedy, passing the epsilon parameters, and then sample according to the Q values. Then we can obtain the action and then make it an output from the agent so that it can pass it to the environment. For the learning, it's basically, I think, first one is updating the target network every so often according to the number of iteration. And then this one is doing the gradient calculation. So it's like D loss, D theta is the, we have the square root of the Q values. We briefly touched that. And then you can obtain the gradient of the loss with respect to the parameter theta. Then we use the optimizer to update the parameters to an online parameters. So this one is like quite simple steps, 3 steps, like update your target network, obtain your gradient, and then update your parameters. The loss is described here. So it's basically, I think we don't need to go to detail here, but basically it's just calculating the TD error we described. So it's like the reward from the next time step plus discounted future Q values, and then take the difference between this target and the current Q estimation. And finally, you apply an L2 loss on that, and then take the mean over the whole batch. Then you have the loss. And this script, I think, describe very comprehensive, all kind of components of a simple DQN agent, which I think is very worthy for all of you to understand the key concept of the DQNs, and also to really make some practical usage of the reinforcement learning agent. Okay. Yeah, so Any like high-level questions on the code walkthrough?
Hi, Prof.
Hello?
What are the environments that in this example? Like what actions and what is the environment in this code's context?
Okay. First of all, let me go back to this. First of all, like the code we just walked through, apart from this line, right? This line really have an actual instantiation of the environment. All of the other part of the code, they are pretty general, so they can be applied to any environment. And on the other hand, you can also sense the same thing from this environment APIs, right? So it does not tell you like it comes in a very abstract level. It has only two key functions. One is reset, the other is step. So reset is like just start the game or the environment from the very starting point, and then the environment can give a timestamp. And then the second function is the step. So the environment can take any action, either from like human player or from the agent. It take the action, feed it to the environment, and then output the next time step. So from this like abstract API, it does not really constrain itself to any specific environments. So all of the properties of the environments can be described in the, let's say, so this one, so the observation spec and the action spec. So for example, your observation can be certain like what 1D vector or like 2D or anything, as long as you can give the shape to the agent. The agent can form a neural network accordingly. For example, here, right? You will flatten the input, walk it through an NLP, produce like the queue of SA over all of the actions. So essentially what you need is like the input shape and then also the output shape. Other than that, I don't think like anything from the environment is necessary.
We need to define the model also, right? How
It's in the network. You mean this one?
how one state transition to another?
It's defined in the inside the environment. The model-free reinforcement learning does not need to know anything about the environment.
Okay, well, for this, if you want to run this code in a specific environment that we make, then we have to define it, right?
You just need to, okay, let me quickly find some example. So you could go to this repo like dm-inc, okay? It describes the thing we just mentioned in the slides. So there's a abstract-based class for the reinforcement environments. If you would like to implement your own reinforcement environment or to incorporate certain existing game to this API, what you really need to do is to let's see, right? Just take you to the actual code example. You can just inherit from this abstract environment, right?
Oh, I see, I see.
So what it really does is that it provides two essential API. First one is reset, right? We briefly mentioned that. The reset just restart the game. And like, for example, here, it can restart like certain y-axis to 0 and then randomly sample an x from the column. And then you output a timestamp. And then the second very important API is the step function. So it takes the action, output the time step. So what you really need to implement an environment are these two essential functions. And what's the observation spec, which is so it uses a class called spec, but I think it's very easily, you can understand the idea.
Yeah.
This is an array. So it can have shape and has some data type, what's the maximum, minimum values of that. And also for the action spec, it describes like the action is a discrete array. The number of value is the number of actions you can perform. So essentially, I think it's super clear and clean example to let you really define your game and to fit it to this general API. For example here, right? You can see the action is left, no op. No op means like just stay there, right? And then so there are three actions so that the agent can know that only three actions it can perform. Yeah.
Okay, thank you so much.
So, and also for the time step, right? For the step function, you can notice the reward specified here, right? And so it's only when it reach certain condition, the reward is +1, and then it will reset, right? So it's very clearly defined in this simple example, and the API is very general, can fit any reinforcement learning environments. And the beauty of this like concise abstract API is that if you write one DQN agent for one simple environment, the same code can be applied to other environments as well. So simply replace this line with any like reinforcement environments which fit the abstract API, and then they can run. Yeah, so it's a very good abstraction of the agent environment interaction, so that people can really develop the agent and the algorithm independent of like thinking about concrete environments.
Thank you.
Okay, another questions? Is there any advice on using continuous space observation and actions? Should we describe discrete tasks? Yeah, there are many ways on the continuous space, also for the actions. So for the input, I think we don't really do anything on them, but there are some pre-processing. For example, some normalization on the input so that the neural network can better learn from the input. But for the action, I think there are ways which you can parameterize the action so that it can fit like Gaussian distribution. For example, you can model the mu of the Gaussian distribution and also to model the sigma of the Gaussian distribution. And then you can learn your policy, which is parameterized by the mu and the sigma. So in the lecture, we didn't touch on the continuous action space, but actually for many ideas can be directly applied to that, including for the DQN paper. Immediately following the DQN paper, there's one very important paper in the continuous control literature. It is called DTPG. So it's essentially using the same experiment repair idea on the continuous control case. So many of these ideas are pretty general, so they are not really restricted to a specific form of input or output. Cool, is that clear? Cool, let's continue. So there are more complete examples in these kind of complete repos. So the first one is the one I just I think I mentioned, this wrapper, the main goal is to replicate the published papers. So all of the papers on the DQN family, including, so I think it's this one, so it's this one, right? Including double DQN, priority play, dueling, and rainbow. They are all implemented in the wrapper, and they really can reproduce the performance of the agent. So it is a very good reference implementation or for all of these DQN agents. You can learn a lot on like how to implement DQN agent, how to because I think we just saw a very simple implementation of the DQN. Much more complete cases can be found in this link. Another very good and clean modular library is called ACME. So it's also from DeepMind. And what ACME really does is that it allows pretty modular isolation of the acting and the learning. And also it really replaced the Python implementation of the replay buffer into a really high performance implementation in C++. So ACME allows you to implement the agent in various kinds of form. It provides many reference implementation, and I think you can run it in a distributed setup. So instead of using like single GPU or single machine, so ACME can really scale up. So these two repos, they are from DeepMind. Basically, they use a library called JAX. So it's a kind of a functional way to write neural network and deep learning. Some of you, I think, might not be very familiar with this library, and it's not that popular outside Google and DeepMind. But I think it's great. I think it's worth learning. We have been using that in CI Lab as well. For the other two repos, they are the reference implementation for I think mostly in PyTorch. So it's more popular, and this one, stable baseline 3, is a very popular one. So it's adapted from the OpenAI baselines. So the OpenAI baseline was a really good reference. However, OpenAI didn't really maintain that repo. So a community picked it up and make the code cleaner and do a lot of like great engineering around that. They provide a very good baseline implementation of various kind of agents there. Another repo is also very popular in PyTorch as well. So it's called Tensho. So the author is actually an intern in the CI Lab. So this repo is great. So I can briefly show it. So it's a very clean code base, implementing like many state-of-the-art reinforcement algorithms. And the code base is tiny. So it's very clean abstraction of the reinforcement learning implementation, allows like high flexibility, and also it keep like high quality software engineering standard. You can learn a lot about the machine learning engineering from this repo, hopefully. And we can briefly walk you through in like how they form the code base. So the first one is the forward. It's basically is the policy, right? You take observation or state from the environment, and the agent produce some action. So it happened in the forward function. And the process function, I think, is secondary. You can really read it in the code how it uses a different process function to form different algorithms. And the learn function is just like given a batch of data. As you can see in the simple DQN case, you can learn from the batch of data. Also provide the post-processing. And then the update is the main interface for training the agent. So it goes from the pre-process function, then to the learning, and then to the post-process. Yeah, and I think it's a great example for reinforcement learning beginner to understand how to write code in a very general sense and how to innovate based on some certain family of the reinforcement learning algorithms. Yeah, cool. Any concrete questions for like what kind of example you should check out after the lectures? So I think these are great examples and which may fit like different people. Yeah, but if you have concrete questions, you can ask it now.
Hi, Prof. You mentioned JAX is functional language.
No, it's a functional flavor, I would say.
Oh.
Yeah, it's in Python.
Oh, okay.
In Python, but in order to for just to work, you have to be a bit careful about so it has to be stateless. So for example, you cannot typically in PyTorch or in typical TF, right? In the module will contain the parameters. So in Jest, it does not do it that way. So in the update function, we just show in the simple Duquesne case, right? For example, in the learner step, right? It takes the parameters as input. Also, it output the parameters. So it's functional and stateless.
Oh, I see.
Yeah, so but they're in Python, so it's not in like Haskell or so the learning curves for Jest or this kind of library, I don't think it's hard because you already have the many examples to base on. Yeah.
What's the advantage of having this functional flavor over normal OOP?
For entry-level tasks, probably not that much of advantages. However, for like large-scale distributed training, and also for like multi-agent training for certain use cases, they are like much more convenient than PyTorch. So for one example, it's like for distributed training and also high performance computing, there's a very convenient function called JIT. Basically, what it does is to transform the Python code you write in the module into some high performance code. So they are executing in C++. So you can write Python code and then just will use the JIT compiler to compile your Python code into high performance C++ code. Also, the Jest JIT can run on many different devices, on CPU, on GPU, or even on TPUs. You can use the same code, and the JIT will compile the same Python code into different hardware. And instead, in PyTorch, all of the code they are in, so all of the like layer by layer of the module, they are executed in Python. So there's some Python overhead. If you really care about speed, that may cause an issue. Yeah, but instead in Jest, they will transform the Python into high performance C++.
Okay, thank you so much.
Yeah, and also for parallel computing, stateless and functional is much more easier. It's much easier to scale up. So if the function is stateless, you can just apply the function on any machine or any device, right? Because it does not really need to store anything. And that allows you to, like, for example, for this add step, you can deploy this same function on, like the same function can be deployed on one device, like single GPU, or even on like thousands of devices, like thousands of CPUs, or even like hundreds of like GPU cards. They can be the same function. But for the stateful function, like in TF, in typical TF and in PyTorch, they cannot do the same thing easily. Yeah, but I think, again, like we provide different reference examples here. So some in Jest, some in PyTorch. You can choose whatever you are more familiar with.
Thank you.
Cool. Any other questions? Yeah, if not, I can continue a bit. May have to speed up a bit. Yep. Cool. The other, so far we have introduced the reinforcement algorithms mostly in the value-based method. So next we are going to spend some time to talk about another big family in the reinforcement learning algorithms. It's called policy gradient methods. So policy gradient method is a way to really directly optimize the policy. So let's first revisit like the goal of reinforcement learning. The goal is to attain an optimal policy to maximize cumulative rewards, right? So for the value-based methods, it's kind of an indirect way to achieve this goal. What it does is to learn the Q values for the state and action, and then choose to form a greedy policy. It is choosing the action with the maximum Q values as the output of this policy, right? So it does not directly parameterize a policy function of pi of s. Instead, it parameterizes the Q values of s and a, and then to use the Q value to infer the policy by taking the arguments over the action, right? So it is an indirect way to obtain a policy. Instead, in policy gradient methods, we do not use the indirect way to first parameterize the Q values and then to transform it to a policy function. We directly parameterize this pi of s function with a parameter theta. And then we optimize this pi of theta according to some objective. For example, here we use j over like pi theta as an objective. We can just directly, just like any other optimization problem, we can define an objective and then use SGD to optimize the policy function. So here is a derivation of the policy gradient methods. I think probably I will not go in details because there are many things in the later part of the talk. So essentially it derived in a way that we can the first function. So we parameterize the policy function as pi of theta, right? And then we take the gradient of the objective j with respect to the parameters theta. And then the j is defined as the expectation of all of the rewards upon the trajectory tau. The trajectory tau is sampled from the policy, and then the objective is defined as an expectation of all of the trajectories. And the goal of reinforcement learning to maximize the total reward, right? So this equation, first equation is describing the same thing. And then after this derivation, you can see first one is expand the expectation into an integral of the probability. And then we can swap the integral and the gradient. You can see like from step 2 to the step 3, basically swapping these two operators. And then later we can use a trick which we will go in detail in the next slide, is called log derivative trick to obtain this equation. And then we can see for the integral, and then this is a probability of the tau, you can transform it back to an expectation. Thus, we can obtain a very essential equation in the policy gradient method, which is the gradient of the policy function is equal to like sum of all the time step over an item, which is taking the log probability of the policy pi over state and on action A. Take the gradient of this log policy function, multiply it by the total reward. So it's a very essential equation in the family of policy gradient methods. So what it is saying that you can have your policy function pi of theta, take the log probability of this policy, take the gradient, weighted by the total reward. So it's quite simple, and actually the formulation was introduced in 1992 or 1993. It's called reinforce. Yeah. So the log derivative trick is comes from forum. It actually comes from a very basic like a derivation in the calculus. So if you recall, like the derivative of a log function is the like x over, so 1 over x, right? So the derivative of log y is 1 over y. So, and then according to chain rule, first you can obtain like 1 over y here. According to chain rule, you should multiply by the derivative of y over x. So you have this simple form, which is the calculus basic operation. And then we can just, instead of putting y, we can put the probability of tau given parameters here. So the same thing, just replace the y. And then you have this equation, and then move this p of tau to the left-hand side, and then move it to the right-hand side. You can obtain this equation, which is basically the step 3 to step 4. Yeah. So this complete the derivation of the policy gradient methods, and actually we provide a simple code example to explain how it really get implemented. So it's a really simple method, and the implementation is quite like concise as well. The very key implementation is actually just this line. So the log probability is the equation in this one, log pi. So it's log pi is the log probability multiplied by the RET is the total return. So it's like just log pi multiplied by the return, make it negative as a loss, and then you can just backplot and use gradient descent to optimize that. So it's really very concise and effective method. And when it goes to adequacy methods, basically, in addition to the policy gradient, so which essentially, I think you can see in this form, like the log probability, and then take gradient. The original policy gradient method only consider as the return. So without this one. So the adequacy method basically is saying that you can use the value estimation of the current state to design the multiplier of this gradient. What is really saying that instead of only taking account the total return, you can leverage another thing, which is the current estimation of the current value estimation of the current state. So by leveraging that, you can judge, like, because the value function is an expectation of the future return, right? So if the current experience return is higher than the expectation, it can have some advantages. So this term is also called advantage in the literature of reinforcement learning. So instead of using the pure return as the multiplier of this log pi gradient, we use the advantage term, which can has many advantages, which is like you can reduce the variance of the gradient estimation, and also you can leverage the estimation of the value to help the policy learning. So to learn the value, very similar to the previous case, you can just apply an L2 loss between the actual collect return and the value function. So there are like two important items in the autocritic methods. First one is to use this weighted form of the log gradient, the gradient of the log policy to update your policy parameters. The other one is to update your value function with the square loss between the return and the value function. Yeah, for this one, we also provide some code example, but we won't go through it for now. Cool. This session was very brief, but I think hopefully it can help after you read the code example. The final one is about scaling up reinforcement learning training, because I think one of the students asked this question in the previous part. I will briefly touch that. So let's review the training time and the training setup in the recent years, starting from the Nature DQM paper. It used to take like 8 days to train a single game in Atari. So even the game look very old-fashioned. They were from 1980s. These games are not simple for the agent. So to train the agent, it took 8 days and even 200 million frames to really make the agent to have human level performance. Back then, researchers were using single GPU for learning, and also use single process to interact with the environment. So everything was quite slow. However, it was the first breakthrough of the deep reinforcement learning. After that, people try various ways to speed up the training, because if this is only one single experiment on one single game, on the full Atari sweep, there are 57 games. So it would take enormous time for researchers to report their progress on the research. People think about various ways, including this one is asynchronous autocritic. So it's using the autocritic formulation implemented in asynchronous way, using 16 CPUs for both the learning and acting. Reduce the training time to 4 days. Also reduce the usage of GPUs. So in some kind of many existing supercomputing cluster, there are a bunch of CPUs. Also in the big companies, there are many CPUs. So people can leverage a huge resources of CPUs to train the reinforcement learning agent. But that's not fast enough. Still 4 days. Then later in 2018, a new method, a new training system was introduced. It's called distributed impala. So it's still an antiquated method, but improved a lot. So now the training time for an Atari game with like 200 million frames can only take 1 hour. So it use one GPU for learning and a bunch of CPUs for acting. Very briefly, the illustration is that you use the learner GPU and with a bunch of the actor in a separate process. The learner will send the up-to-date parameter to the actor. The actor is responsible for interacting between the agent and the environment. After the interaction, the actor will send back the observations to the learner, and they will perform like distributed learning in a simple setup. After that, like compared to the asynchronous antiquated method we mentioned, the previous speed up, so it is the red curve. So this is the new Impala implementation. As you can see from the work clock time, it is so much faster and so much quicker iteration to verify your research idea. So they are very kindly provide like certain code examples in these two DeepMind repos. The first one is a really complete, simple example from neural network library Haiku. The other is from the Acme, so you can check the code out. And finally, time come to like 2020, people realize like there are many advanced, highly parallel devices. For example, Google has the TPUs, and researchers spent a lot of engineering effort to fully leverage the high compute power in the TPUs. They really make the training time like much shorter. Now it can take only like 8 minutes to train an Atari game. So if you recall, like it went from like 8 days to like 8 minutes. So now like with a one TPU, 8 cores for both learning and acting inference, and like a few hundred of CPUs, people can really like verify their research idea, do innovation, do iteration in a matter of minutes. Yeah, I won't go to the architecture. You can check it out in the paper. We can see a summarized table here. As you may notice, like there are like this column is like what kind of hardware they are using, and these are many different kind of spec. What kind of how many environment, how many CPU they are using for this kind of experiment. And on the final column, it noticed like the ratio of the speed up over their reference. So most very notably for this DeepMind lab environment using the CRL architecture, it can achieve like 80 times speed up compared to a single GPU like NVIDIA P100 with with 100 and about 80 CPUs. And for other reinforcement environment, they also achieve like multiple times speed up. So it's like really making the effort to leverage the highly parallel hardware to achieve a much faster training time. Yeah, I think probably for this one we can skip. And for even more complicated training system, they are leveraging like huge resources. You may already immediately notice from reading from the illustration, they're using like in the OpenAI 5 highly compressed distributed training system. For only running the game simulation, they're using like 51,000 CPUs to simulate a game, and to forward the policy network, they're using like 512 GPUs, and to learning from the experience replay buffer, they are using another 512 GPUs. So that they can achieve like super high throughput for the whole training system. And even so, they have to train the agent for a matter of months. So because the game is highly complex, it's the Dota 2 game, they have to leverage this very high throughput training system so that they can train their agent only from the data and only from the agent environment interaction. But I think the good news is that all of these components, they are essentially the same as what you have been learning from the lecture. So the key concept is still like experience replay, the learner iterate through the iterations, and then the agent environment interaction happen in the lower worker, which is collecting the experience. And then the forward GPU is just doing the like agent dot step. So essentially the central API are the same, but it requires like another level of like distributed training system, like the knowledge of the highly skillful implementation of that. But the key idea of the reinforcement learning, they still apply in the highly complex training system. Similarly, for AlphaStar, they are leveraging like TPU for the learning and for the acting, but in a high level, this is similar to the actor-created methods. So the learning is upon a queue of trajectories from the experience from the environments. So they are from the algorithm side, they have innovation in multiplayer. However, for the single agent training, it's nothing really fancy. So they are basically using the Impala paper with the V-trace correction on the return. So they are still in the actor-created methods family. Here we list like two distributed reinforcement learning and machine learning libraries, which can help you to implement this kind of complex distributed system in a much easier way. So don't be afraid of the distributed system. They can be made really easy with the help of these libraries. So I think we are now out of time. So here is my contact method of my email and my homepage, also some webpage of CLI Lab. You are welcome to check them out and feel free to ask me any questions about reinforcement learning. Yep. So that's the end of the lecture.